All right, let's look at inverse derivatives. Not necessarily looking at inverse trig functions, although this approach could be used to find the inverse trig derivatives. So a few notes about a function and its inverse. And this is all pre-cal type stuff, but f of f inverse is the same as f inverse of f, and both of those will equal x, and that's kind of your definition of an inverse. It undoes the original. When given f of x, you find the inverse by swapping x and y and solving for y in the new equation. The x value of the inverse is the y value of the original function f of x. We'll use that property later. And the third one, which doesn't show up much in AP Cal, but it is true that the graph of the inverse is the graph of f of x reflected across the line. Go away! Across the line y equals x. So, putting this into practice, oh, whoops, not yet. Let's look at a quick proof of the formula that we're going to use when finding the derivative of the inverse. Sometimes I shy away from proofs because they tend to be like really long and cumbersome. This one, not so much. So we're going to start with that basic property that f of f inverse of x is equal to x, and we will start by doing the derivative of both sides of that equation. So we're going to do the derivative of the left and the right. When I do the derivative of the left side, that will be a chain rule. So we're going to start on the outside, do the derivative of the outside f first. We'll leave the inverse alone. That's the inside. So it's f prime of f inverse. Then we multiply by the derivative of f inverse, which technically you could write f inverse prime like that, but that looks kind of stupid to me. So when I do the derivative of f inverse, I like to write it as the derivative ddx of f inverse of x. And so that's the derivative of my left side. That's just a chain rule. F prime of the inside times the derivative of the inside equals, and then on the right side, the derivative of x with respect to x is 1. And then we're trying to isolate this part, the derivative of f inverse, and we'll do that simply by dividing by this stuff over there. So my final answer, and this is the proof, the formula we will use for the derivative of f inverse of x is 1 over f prime of f inverse, whoops, I wrote that wrong, f prime of f inverse of x. And that is what you would be better off just remembering. Because if you don't remember that, then you have to work through this proof to generate it every time, although it is just a two-step proof. All right, so now putting this inverse stuff into practice, let's do a quick review of pre-cal type information. If you're given a table of values and you need to find f inverse of 7, do remember that the x coordinate of the inverse is the y coordinate of the function. And so I'm looking right here, and we know that f of 5 is equal to 7. That means that f inverse of 7 is equal to 5. And so there's your answer. F inverse of 7 is 5. Don't confuse this little -1 with an exponent. It's not the reciprocal, and some lousy teachers out there do use the phrase or the words inverse and reciprocal interchangeably, but they are not synonymous, and so you do not do anything with the 2/3. That is completely irrelevant when we're finding f inverse of 7 given this table. So just remember that. Find f inverse of 4 if f of x equals all of this stuff. And remember, if f inverse of 4, that means y equals 4 for f of x. And so what I'm going to do here, I'm not going to actually find the equation of the inverse. I'm just going to say that if y is equal to 4 for f of x, that means I can take this equation, set that equal to 4, and solve that. And so I'll move my 4 over, x squared minus 3x plus 2 is equal to 0, factor x minus 1, x minus 2 is equal to 0, and we actually get two solutions, x equals 1 and 2. So what I know is that f of 1 is equal to 4, and f of 2 is equal to 4, because those are the solutions to my original equation. That means that f inverse of 4 would actually have two values. F inverse of 4 would equal 1, and f inverse of 4 would equal to 2, which I just now realize that means there's a slight inconsistency with my notation, because if I write f inverse like that, I'm kind of implying that the inverse is a function, However, I just showed that the inverse has two y coordinates associated with the single x coordinate of 4. So in this case, the inverse is not a function. However, those will be the two values of x in the inverse. I'm sorry, the two values that f inverse of 4 could possibly equal. So moving on and applying this to calculus, so we have a table below that gives select values of a differentiable function f of x and its derivative f prime. I want to find the slope of the line tangent to f inverse at x equals 4. And if you are finding the slope of a line tangent, you will need the derivative. So in other words, we need the derivative of f inverse of x at such that x is equal to 4. And I know that the formula for f inverse is going to be 1 over f prime of f inverse of x, but in this case I'm plugging 4 in the place of the x. So 1 over f prime of f inverse of 4, and then it's just a matter of applying this, using that formula and figuring out what the values are. So I'm going to start by finding f inverse of 4, and again that means that y is equal to 4 for my function, and I'm looking right here. I see that f of 2 is equal to 4. That means, therefore, f inverse of 4 is equal to 2. So I can go back up here to my formula thing here. That's going to be 1 over f prime of 2. And f prime of 2, that's straight in the table. F prime of 2 is 2/3. So it's 1 over 2/3. And if you're really smart, you can call that 3/2. So there is the slope of the line tangent to the inverse at x equals 4. Okay, let's look at this one. Here I gave you an equation for f of x, and I want the equation of the line. Equation of a line. You should immediately be thinking point and slope. Point and slope. Every single time you write the equation of a line, that's what you need. Okay, so the equation of a line, normal to the inverse at x equals -5. So let's start by getting the points, because more often than not, the point is the easy part. So I need f inverse of -5. And to do that, I'm going to have to think, what makes my function equal to -5? So my thought process is, what makes f of x equal to -5? There's my question. Well, f of x is x cubed plus 3 equals -5. Let's move that 3 over. X cubed equals -8, and x would equal -2. That means that f inverse of -5 is -2. And so I have my point, -5, -2. Now I need to get my slope. And the slope is going to be that formula. It's the derivative of the inverse is 1 over f prime of f inverse of x. That's my general formula. And then at x equals -5, we need to evaluate 1 over f prime of f inverse of -5. And we've already figured out what f inverse of -5 is. That's -2. So that's going to be 1 over f prime of -2. And then to get f prime of -2, well, I don't have a table to pull the value from this time, but I do have a function f of x. And so now I'm going to kind of come over here, and I'm going to think, okay, what is f prime of x? F prime of x, well, that'll just be 3x squared. F prime of -2 is going to be 3 times -2 squared, which is 12. And so this is going to be 1/12. But that was the slope with the derivative. That's my tangent slope. The problem asks for the equation of the line normal, and so that means my normal slope is going to be -12. So my normal slope equals -12. And then once I get the slope, I have my slope, I have my point, -5, -2. The equation of my line is y minus -2 equals my slope times x minus -5. And so there is our normal line to the inverse using that formula, 1 over f prime of f inverse. Then my last question, I believe, is the last one. Let f and g be differentiable functions such that f of g of x is equal to x, and then all of this other stuff. We need to find g prime of 3. There are a couple of ways we could do this. I'm going to start by recognizing this right here, because inverses are defined such that the composition of the function and its inverse will give you x. So if they tell you that f of g of x is equal to x, that's a fancy way of saying that f and g are inverses. So they may not explicitly tell you that it's an inverse problem, but you need to recognize that property. So f and g are inverses. Okay, which means that f inverse of x is equal to g of x, and g inverse of x is equal to f of x. And so that's a true statement. F inverse is g and g inverse is f, and so I'm thinking about that. They want you to find g prime of 3. Well, if they ask you to find g prime of 3, before you're allowed to plug in 3 to the derivative, you must first find g prime of x. So I'm making a note to myself, I need g prime in terms of x first. Then I will deal with the rest of this information. Okay, so that brings in the question of how do you get g prime of x, and there are a couple of ways you can do it. You could actually do the derivative of the original equation right here that I have in red box. I'm going to go a slightly different route. Because I do want g prime, I want to use an equation that has actual g of x in it, this red box one being one of them. The other one, and this is one I'm going to use, is this equation right here, where f inverse is g. So I'm going to go with that. And if g of x is equal to f inverse of x, which I had written here, then that means that g prime of x is the derivative of the inverse, which again is that formula, 1 over f prime of f inverse of x. And the question's asking, what is g prime of 3? So now that I have an equation for g prime of x, I can plug 3 into that. G prime of 3 is going to be 1 over f prime of f inverse of 3. And once again, it's a matter of being able to evaluate this. Starting on the inside, I need f inverse of 3. And f inverse of 3 is going to be where f of x is equal to 3. So when does f of x equal 3? And that happens right here at -1. So this becomes 1 over f prime of -1. And so the question now is, what is f prime of -1, which is given to us up here. Again, f prime of -1 is 2, and so I get 1 over 2, and that is our answer. We wanted g prime of 3, and there is g prime of 3. So that is it for inverse functions, or inverse derivatives, that is.